Good morning, everybody. Welcome. Today, we're delighted to have Marcelo Disconzi from Mathematics Department at Vanderbilt University. And let me introduce Marcelo a bit. So Marcelo works on so many topics. It started mainly with partial differential equation, mathematics of fluid dynamics, mathematics of general relativity, geometric analysis, and of course mathematical physics, in a broader sense. So some of his notable recent works are, the rough solution for the Euler equations and non-relativistic Euler equations, and also in the extension of that, developing methods to handle the rough solution for the relativistic Euler equations as well. And currently, he is interested in, the free boundary Einstein-Euler system. And today he's going to talk about, another topic which is also very interesting, general relativistic viscous fluid. So take it from there, Marcelo. Yeah.
Thank you, Oscar, for the very kind introduction. So thanks to the organizers for the invitation, the audience for being here. Today I'm going to tell you about a series of works that have been obtained with several collaborators listed here. Let me mention, if you have any questions during the talk, you just feel free to interrupt me. You don't have to wait until the end to ask questions, okay? Well, the topic of this talk is relativistic viscous fluids, but let me start with the case of relativistic ideal fluid. Ideal means without viscosity. I believe that everything on this slide is going to be known to everyone, so I'm going to go over this slide quickly and use this just as a way of setting up my notation and conventions. So an ideal fluid is described by the relativistic Euler equations written here, where T is the energy momentum tensor and J is the baryon current. So they are given by these well-known expressions. And my notation is as follows. Rho is the fluid's energy density, or sometimes I say simply the density. N is the baryon density, and P is the pressure. The pressure is given by an equation of state, which means that there is a known function of the density and the baryon density, and which function you choose depends on the nature of the fluid. So U is the fluid's velocity, which is a time-like vector field normalized to unity, and G is the space-time metric. So the space-time metric can be given if you are working on a fixed background, or you can consider coupling these two Einstein equations. Nabla is just the covariant derivative. Now, as I probably don't have to explain to this audience, the relativistic Euler equations are essential in the study of many physical systems of importance in astrophysics, cosmology, and high-energy physics. What perhaps might not be known to everyone is that there are also important situations where we need a theory of relativistic viscous fluids. We need a theory of relativistic fluids with viscosity. So what I'm going to do next, I'm going to motivate this by just give you two important examples where viscosity is important. The first example that I want to discuss is that of the quark-gluon plasma. So the quark-gluon plasma is an exotic state of matter that forms when matter deconfines under extreme temperatures and densities. Now, how extreme are the temperatures? Maybe the actual number here doesn't mean much for many people, but just as a matter of comparison, this is several orders of magnitude higher than the temperature of the sun. And these temperatures are actually obtained in collision of heavy ions in particle accelerators. So they're actually obtained in experiments. Therefore, the study of the quark-gluon plasma gives the community a great opportunity to understand the properties of matter under extreme conditions. The quark-gluon plasma also offers a window into the earliest moments of the universe, because it is believed that microseconds after the Big Bang, the universe was filled with matter in the form of the quark-gluon plasma. So I don't have time to give you the whole history of the quark-gluon plasma and why it's important, why it's exciting, but I may just remark that the discoverer of the quark-gluon plasma was named by the American Physics Society one of the 10 most important discoveries in physics in the first decade of this century. So that was a big deal. Now, through a very rich interaction of theory, experiments, numerical simulations, and phenomenology, a coherent picture emerged, showing that the quark-gluon plasma is a relativistic liquid with viscosity. So here are some plots, and you don't have to worry right now about what exactly I'm plotting here. I mean, they are plotting. This is not my plot, of course. Let me just point out that here you have the dots are experimental data, and the curves are theoretical curves. They are kind of theoretical predictions. And you can see that the curves and the data match pretty well, but that is the case only if we include viscosity in your model. Okay, so if you try to fit this data using the relativistic Euler equations, it's going to be way off. You cannot reproduce this data using an ideal fluid. So that's one example where you need viscosity in your theory. Another example where viscosity can be important is in the study of neutron star mergers. For a long time, it had been assumed that you could model a neutron star merger using the Einstein-Euler system. However, this assumption has been recently revised by Alford, Bovar, Honowski, Rezzolla, and Schwenzer. So let me explain what they found out. Their results can be more or less summarized as follows. First, they get an estimate for the characteristic macroscopic scale of the system, which is associated with gradients of the fluid variance. And they do that by running some state-of-the-art numerical simulations of general relativistic ideal fluids. Okay, so they run these numerical simulations of ideal fluids to get an estimate for the macroscopic scale of the system. And then they also get an estimate for the characteristic microscopic scale, and for that they rely on microscopic theory. Now, once you have this an estimate for these two scales, you can go ahead and compute something called the Knudsen number, which is the ratio between the microscopic and the macroscopic scale. And what they find out is that there are situations where the Knudsen number is not small. This implies that viscous contributions then are likely to affect the gravitational wave signal emitted by the merger of binary neutron stars. So why is that the case? So when you derive the fluid equations from microscopic theory, you do that essentially by an expansion on the Knudsen number. You do an expansion on the Knudsen number. The zero order contribution is the ideal fluid. So for you to, if you just work with the ideal fluid, you mean that you are ignoring everything else on the expansion, but because it is an extension on the Knudsen number, it means that the Knudsen number has to be very small for you to be able to ignore all these corrections. If the Knudsen number is not small, you cannot truncate your expansion at the zero order. You have to include at least the first order, maybe higher contributions. And when you are including the first order contributions in the Knudsen number, those are precisely the viscous effects. Okay, so that's why if the Knudsen number is not small, viscosity is important. More recently, a second independent argument favoring viscosity in neutron star mergers was obtained by Most, Harbour, Harry, Zhang, Alford, and Noronha. And what they did, they studied in very much detail the microphysics of neutron star mergers. And what they find out is that the remnant settles in a regime which is described by viscous fluid dynamics. And they also show that that causes a shift in the gravitational wave frequency during the ring down stage. So in sum, the message here is that neutron star collisions are intrinsically viscous. And this is not just something theoretical. These authors also explain why the next generation of gravitational wave detectors is going to actually be able to probe the contributions of viscosity in neutron star mergers. So we have two important examples that I gave of situations where viscosity is important. So then the question is, how can we model viscous contributions in a relativistic fluid? So the starting point usually is like Matter models is the energy momentum tensor written here. where rho, u, and p are as before. Capital pi is just an abbreviation for this quantity, which is the projection to the space orthogonal to the velocity. But compared to what I wrote before, compared to the ideal fluid, there are some new quantities, which are the viscous fluxes. So these viscous fluxes are the viscous correction to the density, the viscous correction to the pressure, the heat flow, and the viscous shear stress. Okay, so these are supposed to model all the viscous contributions to our fluid. The pressure continues to be given by an equation of state. And for simplicity, for the rest of the talk, I'm going to assume that the pressure depends on the density. Okay, just for simplicity to make to write last equations. Now, of course, this is just a formal expression. To really define a theory of relativistic viscous fluids, I have to specify what these viscous fluxes are. I have to tell what they are to really define the theory. Now, there are many ways you can do this. Those are sort of modeling choices. But basically, you can classify the type of modeling choices that people have used in the literature in two classes. So let me explain the two types of choices that people use. In the first approach, that leads to what are known as first-order theories, the viscous fluxes are given in terms of the density and the velocity and their derivatives. So this is very much like what you do in classical Navier-Stokes equation. In the classical Navier-Stokes, the viscous shear stress is given by some expression involving derivatives of the velocity. So here is something similar. And I'll be giving examples in the next slide, okay? So to make this more concrete. So in this case, the equations of motion are, as usual, the divergence of the energy momentum tensor, possibly coupling to Einstein equations. In a different approach, also using the community, this approach leads to what are known as second-order theories. The viscous fluxes, there are going to be some new variables that are to be treated on the same footing as the density and the velocity. Okay. In this case, the equations of motion are going to be, again, the divergence of the energy momentum tensor equal to 0, possibly coupling to Einstein equations, but you have to supplement the system by further equations that are going to be satisfied by the viscous fluxes. This makes sense because if I'm not saying, if now I'm saying that the viscous fluxes are new variables, I need new equations to get a closed system. Okay. So before I give you examples, let me just summarize in a nutshell. In first-order theories, the viscous fluxes, for example, the viscous shear stress, is some known expression involving the density, the velocity, and their derivatives. In second-order theory, the viscous fluxes, for example, the viscous shear stress, is going to satisfy its own equation of motion. So this is the summary. Let me move on to give you concrete examples now. The first example of a relativistic viscous fluid theory goes back to Eckert in the 40s, and soon after also by Landau-Lifshitz in the 50s. Their theory is a first-order theory defined as follows. We set the viscous correction to the density equal to 0, and then the viscous shear stress and the viscous correction to the pressure are given by these expressions. So these expressions are complicated. The details are not important for this talk. I'm just writing here so you can see. The only thing that I want to point out in these expressions that there are two coefficients that appear, eta and zeta. These coefficients are going to be functions of the density, and they are the coefficients of shear and bulk viscosity. So again, this is similar to classical Navier-Stokes equations where you have shear and bulk viscosity. And here, for simplicity, just to save the space on the slide, I'm setting the heat flux to 0. So how did these authors arrive at this formulation? In essence, they were looking for a covariant generalization of the Navier-Stokes equations, and they made modeling choices that enforce that the entropy production is non-negative. Okay, so these are two very natural requirements, two very natural things that you could try to construct a theory. But despite it being natural, this does not work. So the reason why this does not work is that the Eckert and Landau-Lifshitz theories, they violate causality. They allow for faster than light signals. Okay, so, and of course, that's in contradiction with the basic postulates of relativity theory. Mathematically, what is behind this is that the equations of motion turn out not to be hyperbolic. Okay, they turn out not to be hyperbolic. Moreover, these theories are also unstable, and stability here is in the usual sense of just mode stability. Okay, so if you analyze the plane wave solutions, which are perturbations of a background solution, and you look at the modes, these theories turn out to be unstable. Moreover, this instability in acausality results, they apply not only to Eckert and Landau-Lifshitz, they apply to a large class of first-order theories. I don't have time to go into the whole history, because as I said, this starts in the 40s and 50s, but the message that I'm trying to convey here is that it turns out that it is difficult to construct causal and stable theories of relativistic fluids with viscosity. Okay, and a great deal of work has been done to try to address these issues. Okay, so that was one example. Let me move on to another example now. That's going to be the Israel-Stewart theory. The starting point, again, is the energy momentum tensor. This theory is a second-order theory. It was introduced by Israel and Stewart back in the 70s. It's actually based on a work of Miller from the 60s, which did something similar for classical fluids. So sometimes we call this theory Miller-Israel-Stewart. Although the modern versions that people actually use are slightly different and are due to different authors. Okay? But I'm just going to call all of them Israel-Stewart for simplicity. Now, how is this theory defined? The equations of motion are given by, you set the viscous correction density to be 0. Again, you have the divergence of the energy momentum tensor equal to 0. But remember, now this is a second-order theory, which means that the viscous fluxes are new variables. So I have to postulate new equations of motion. And the equations of motion that are postulated are written here. They are complicated. The details of all these terms, they don't really matter for the sake of this talk. I just want to point out that all these equations, they have the form of relaxation type of equations. Relaxation type of equations because the intuition here is that if you take a system in thermodynamic equilibrium and you perturb the system, then because of viscosity, it's going to dissipate energy, so the system should relax back to equilibrium. So that's why you have this type of equations. In particular, here you have some coefficients tau, which are relaxation times, which basically set the scale, the time scale for which the system relaxes back to equilibrium. Okay. Now, in this equation, there are some extra terms here that I'm not writing what they are, but if you go to the actual papers and look what they are, in general, they can involve derivatives of all the variables. Now, this is a first-order system of equations, so from the PDE point of view, all these terms here, they are top-order terms. They're top-order terms. And this tells that the Israel-Stewart equations, they form a very complex system of equations. So this is a very large system with non-diagonal principal part. So how large it is, if you include all the fields, this is going to be a 26 by 26 system with non-diagonal principal part. So it's going to be a very, the mathematical analysis of these equations is very difficult then. Nevertheless, despite being complicated, people were able to say quite a few things about these equations. First, stability holds. So these equations are stable. So that's good. And if you look at the linearization about global equilibrium, those equations are causal. Okay, so which means the following: global equilibrium is a state defined as density and velocity constant, and all the viscous flux is vanishing. So if you linearize about these states, then you get a linear system of equations, and in that system you can show that it's causal. Causality has also been proved in 1+1 dimensions and in rotational symmetry. And finally, the Israel-Stewart equations, they have been very successful in applications to the study of the quark-gluon plasma. So if you go back to those numerical simulations that I mentioned, these theoretical curves are done with numerical simulations of the Israel-Stewart equations. Okay, so, oh, shit. Sorry, I should go back here. Okay. So in sum, the Israel-Stewart equations are good for many applications. Okay, so that's a very good theory. However, there are important questions that remain open. One is that of local opposedness, right? You want equations that are local opposed. So local opposedness, for maybe for people in different fields, simply means the following: the local opposed of the Cauchy problem. So given initial data, you want to prove that a solution exists, taking the initial data, and the solution is unique. Okay, so it's the standard existence and uniqueness of solutions. Also, we want to know about causality of the equations in 3+1 dimensions without symmetry assumption. And notice that the causality that I mentioned before was only for the linearization about this specific type of states. Okay, so we want to have a general causality result without symmetry assumptions. So, and these are the questions that we address in our theorem. So here's the first result I want to state today, which says the following: the Israel-Stewart equations are causal. The Cauchy problem is locally well posed in Gevrey spaces, and in the particular case where these two viscous fluxes, the heat flux and the viscous shear stress, are absent, then local opposedness in fact holds in Sobolev spaces. Now, for the non-mathematicians, let me just point out, I'm not going to define what the Gevrey Sobolev spaces are, but when you prove local opposedness, you always prove in a certain function space. There's a certain function space, which is the space where solutions belong to. Then you have these two types of function spaces, and let me just point out that Sobolev spaces usually are the spaces we are interested in. They are much more general than Gevrey spaces. And I'm going to make a few more comments about this later. All these results, let me point out, they hold with or without coupling to Einstein equations. Okay, so that's the result. Let me just make a few comments on the proof. Let me start with causality. Some people might be thinking, so what is the big deal with causality? All you have to really do is compute the characteristics of the system, right? Causality basically boils down to find the characteristics of your equations. But remember, these equations are very complicated. So if you just try to compute the characteristics by brute force, probably you're going to go nowhere. At least we got nowhere with that, right? So what we had to do, we had to think a little bit more geometrically. We have to develop some calculation techniques which are guided by this concept of acoustical metrics that appear in the case of an ideal fluid. And notice that I put plural here, metrics. That's because this is a system with multiple characteristic speeds. So there is going to be more than one metric associated with it. Now, for local opposedness, what we do, we derive estimates using techniques of weakly hyperbolic systems. These are techniques that go back to the celebrated work of Leray and Nomiya in the 60s. And here is where we have to use Gevrey spaces. We have to use Gevrey spaces to avoid loss of derivatives. The reason we have to do this is because we, unfortunately, we were able to show only that these equations are weakly hyperbolic. If they are weakly hyperbolic, you cannot close the estimates without derivative loss unless you work on a very regular space like this. However, in the simpler case where the heat flow and the shear stress are absent, then we can actually close the estimates in Sobolev space. That's just because the equations simplify a lot in this situation. Okay. So this is just a kind of sketch of the proof. Now, let me point out something very important. Throughout this talk, I'm going to always state my theorems in a very informal way. So I'm not going to state all the technical assumptions and so on. So, but of course, there are some specific quantitative assumptions that go into these theorems. In particular, this theorem that I just stated to you, it holds under suitable assumptions on scalar quantities of the problem. So there are certain inequalities that need to be satisfied for the theorem to hold. So here is just an example of one such inequality. You don't have to worry about what all these symbols actually mean. I just want to write one example for you to see that there are certain inequalities that go as assumptions in the theorem. But what I want to remark is that we also derive some inequalities that are necessary conditions for causality. So there are certain inequalities that we derive. Here's an example. Again, the specific meaning of all these symbols right now doesn't matter very much. All you need to know is that there are certain inequalities that we derive that, if violated, imply that the system is not causal. So they are necessary conditions for causality. Now, these necessary conditions are very interesting because all the quantities that enter in these inequalities turned out to be things that people compute in numerical simulations. So now you can go back to the numerical simulations and you can test at each time step if these inequalities are violated or not. And this is something that was done by two different groups of authors listed here. So they went back to the standard simulation of the quark-gluon plasma, and they found out the following. They found out that in these numerical simulations, up to 30% of the initial fluid cells violate causality. So these simulations are actually being run with causality violations. Now, as you can imagine, that doesn't sound like very good news. Now, what exactly you do with that result? Does that mean that you should completely distrust the numerical simulations, or there are parts of it they can still trust, and so on? That's a discussion that I leave for the physicists that work on this. But if nothing else, what I think this result does is that it should work as a cautionary tale. A cautionary tale for the risks of running numerical simulations on equations whose mathematical properties are poorly understood. Okay. Anyway, so that's a kind of bit summary of results on the Israel-Stewart. Now let me just go ahead and point out some potential limitations of this theory, and that's going to be going to open the door for what I'm going to discuss in the second part of the talk. So first, it's not known if Israel-Stewart is applicable to the study of viscous effects on neutron star mergers. When I say that's not known, I mean two things. First, we simply don't know if that's the correct model. It could be that the actual model is something different. But also on a more technical level, when you talk to people who do general relativistic numerical simulations, what people from the numerical community are going to tell you is that to run their algorithms, to run their numerical simulations, you need the equations to satisfy several properties. And one of the properties that they want is a local oppositeness in Sobolev spaces, which is lacking for Israel-Stewart. Remember, we were able to prove local oppositeness only in the case where the heat flow and the shear stress are absent. Okay, so in general, we don't have a local oppositeness in Sobolev spaces for Israel-Stewart. There are also situations in heavy ion collisions where it is not known whether or not Israel-Stewart is applicable. There is this issue that I told you about, that we might have to make a reassessment of numerical simulations in light of these causality violations. And finally, it is known that Israel-Stewart has some difficulties in describing shocks. Okay, and so this is a fluid theory. One of the things that we like to do with fluids is to study shocks, but that's difficult to do with Israel-Stewart. So all in all, the message here is that there is enough motivation to look for alternative theories. Okay, there's enough motivation to look for alternative theories. So what I'm going to do next, I'm going to tell you about a different theory that we can also prove some things. So the next theory that I want to discuss is the BDNK theory. So this is a first order theory, which is the culmination of several works by different people. And it's defined as follows. Starting again with the energy momentum tensor, this is going to be a first order theory, which means that the viscous fluxes, there are going to be some known expression of the density velocity in their derivatives. And in the BDNK theory, the viscous fluxes are defined by these very complicated expressions. Okay. Now, you don't have to worry too much about the details of all these complicated expressions. But of course, this is not the kind of thing that you wake up one day in the morning and just guess. Okay, there is a reason why they are defined this way. I'm going to tell you a little bit more about this later. Okay, so for now, let me just define the theory, which is given by these viscous fluxes. Now, as a matter of comparison, this first order theory has many more terms compared to the Eckert-Landau-Lifshitz theory. Okay, so just as a simple comparison, if you go back to Eckert-Landau-Lifshitz, for example, the viscous correction to the pressure here is given only by the divergence of the velocity. In BDNK, the viscous correction to the pressure still has the same term, the divergence of the velocity, but has all these other terms appearing here. Okay, so it's something much more complicated, but we need all these more complicated terms to fix the causality and instability problems of Eckert and Landau-Lifshitz. Okay. So what I'm going to do now is the following. So let's take this as given. So this is the definition of the viscous flux for the BDNK. Let me tell you what we can prove with that, and then I'm going to make a few comments on where these expressions are coming from. Okay, but let me first tell you what we can prove. So here is another theorem. The statement is that the BDNK equations are causal and stable. The Cauchy problem is locally well posed in Sobolev spaces. And these results, they all hold with or without coupling to Einstein equations. Okay, so this is the result. Let me tell you just a few ideas about the proof. For causality, again, we have to study the characteristics of the system. Like for Israel-Stewart, these equations are very complicated. Brute force is unlikely to succeed, so we have to think a little bit more geometrically. For stability, what we do, we prove a new theorem that connects stability and causality. Okay, so, and then once we prove the theorem, we can use that theorem to establish the stability of BDNK because we already proved causality. Let me point out that this theorem has later on been generalized by Gavassino. Now, for local opposedness, this system does not have diagonal principal part, but what we do, we diagonalize the principal part of the system. And we can do it basically because we understand the characteristics in detail. Now, there's a caveat that the diagonalization is actually the level of symbols. So to really pass from the symbol to the PDE, the symbols now involve some rational functions. So when you write this as PDEs, you actually have to do pseudo-differential equations. You have to work with pseudo-differential operators. And then there are some technical difficulties we have to address. This is a quasi-linear problem. So that means that we have to do the pseudo-differential calculus for symbols with limited smoothness. But if you do things carefully enough, you can handle that. Let me point out that this theorem actually works if you have a baryon current. Okay, I was ignoring the baryon current, but I just want to point out that this theorem is very general. It also includes a baryon current. Okay, now this is very nice, but let's say what some of the physicists in the audience probably want to know is that, okay, we have this theorem, there's a mathematical theorem, but does BDNK actually give you some interesting physics, right? So can you connect the BDNK theory with physics? Because if you cannot, that's just an interesting mathematical result. And the answer is that yes, we can connect BDNK with physics, with actual physics. First, it can be shown that entropy production is non-negative. You have to understand this statement in its proper context. I can tell you more about later if you want to know, but that's correct. And the BDNK tensor has been derived from both kinetic theory and the holographic principle. Now, let me point out that holography is something that's way outside my field of expertise, so don't ask me about that, but I thought that I'll still mention this because I think it might be interesting for the physicists in the audience. Now, if you really want to get a detailed description of how this theory behaves, beyond qualitative arguments, you really have to run numerical simulations, right? So you really have to run numerical simulations. And numerical simulations of the BDNK theory have recently been done by Pandya, Most, and Pretorius, and Bentilon, Bay, and Figueras. So let me just tell you a little bit about their results. So here is a snapshot of a simulation. So here I'm showing the density for a conformal fluid in one dimension. And the curves here, the solid curves are the BDNK theory, and the dots are Israel-Stewart. So here in the first plot, this is for small viscosity, and you see that for small viscosity, BDNK and Israel-Stewart basically give you the same result. Okay, they basically agree. The second plot is for large viscosity. So for large viscosity, BDNK and Israel-Stewart are very different. But when viscosity is large, you are probably already outside the regime where you should be trusting either of these theories. Okay. So these are results by Pandya and Pretorius. Now, Bentilon, Bay, and Figueras, they found something, again, for a conformal fluid in one dimension, something similar. Basically, they found that BDNK and Israel-Stewart more or less agree, where they are supposed to be a valid description. They disagree where you shouldn't be trusting either theory anyway, and they also disagree in that case with the underlying macroscopic theory. So this now is a two-dimensional simulation of a conformal fluid in the BDNK theory. This is by Pandya, Most, and Pretorius. And what they simulate here, they simulate the evolution of a Kelvin-Helmholtz unstable initial condition. They do this for different values of viscosity. The first column is, in fact, the case without viscosity. So the first column is the ideal fluid. And you see that it happens what it should be happening for an ideal fluid. You just start forming a lot of vortices. But then when you start increasing viscosity, here each column is a larger viscosity, eventually the viscosity simply shears away of the vortices. So that's more or less what your intuition would expect that viscosity should be doing. Now, all these results that I told you are for a conformal fluid in one or two dimensions. So here's a simulation by Pandya, Most, and Pretorius, again in one dimension, but now this is for a fluid with an equation of state of an ideal gas. And in this plot, they are studying the evolution, the effect of heat flow on the evolution of the temperature. So they start with some peaked temperature and evolve, and you see that what happens first, this peak starts spreading. So that's very much like what happens for the heat equation. But these equations now are hyperbolic. So not only this spreads like the heat equation, if you look carefully, this starts forming oscillations, right? So there is this wave-like behavior now for the evolution of the temperature. So there's the spreading, which is like due to the heat flux, but there is also the wave behavior, which is forming this little wave-like forms here on the picture. Now, this is just a very small sample of the results. If you look at these numeric simulations, there are many more interesting things they did. They study shocks. They study a lot of interesting things numerically. But the message is that basically BDNK does reproduce known or expected physics. So this is a physical theory for which we can prove those mathematical results that I told you about. So in sum, the BDNK theory has many of the good features of the Israel-Stewart theory, plus a good local opposedness theory in Sobolev spaces, which is lacking for Israel-Stewart. And as I mentioned, is the kind of thing that you want for applications to neutron star mergers. Okay, so now going back to what I said before, so you don't just guess the form of the BDNK tensor one day. So where is that coming from? Let's say the big idea here is the following. We want to let the fundamental principle of causality dictate which terms are allowed in the theory, rather than making otherwise convenient or natural choices and only later investigate causality. So the latter situation is precisely what happened with Ekman and Lifshitz, right? So they make some modeling choices which look very convenient, look very natural, but only later on people found out that they violate causality. And here we are trying to enforce causality from the get-go. Now this is a bit philosophical, how we do that in practice. Well, it's a long story. I can tell you more about it during the Q&A, but essentially we need to find the correct hydrodynamic frames for this theory, okay? So the story here is that when you're writing a fluid theory that's out of equilibrium, there is a certain ambiguity in the definition of what you mean by temperature, density, and so on, okay? So there is not a unique definition for these quantities out of equilibrium. And these choices are called, for historical reasons, hydrodynamic frames. And what you have to do then, you have to explore this ambiguity to try to find the correct choices of hydrodynamic frames that are compatible with causality, instability, and so on. Okay. Now I know that this is like, you know, very high level, doesn't give you much details, but again, it's a long story, it's a bit technical, and I can tell you more about it later if you're interested. Okay, but that's sort of the philosophy underlying the construction of the BDNK tensor. Pushkar, how much time do I have?
You still have around like 17 minutes.
Okay. So I'll try to finish quickly to leave time for questions then. But
yeah, so, it's okay. You can take like 5-10 minutes extra.
Okay, yeah. So let me just tell you a little bit now about another result. So again, these are fluid dynamic equations. One thing that we like to study in fluids are shocks and singularities. Now for Israel-Stewart, remember I told you, this is a result that go back to previous authors, Gerlock, Lindblom, also in Hitchcock, that there are no physically acceptable strong viscous shock profile solutions for Israel-Stewart. And you cannot really talk about, I mean, maybe you can, but not with the standard techniques, you cannot talk about weak solutions for Israel-Stewart because they're not in divergence form. So you'd have to come up with a different formulation of what you mean by weak solution if you want. For BDNK, the first investigations of viscous shocks have been done recently by Freistuhler and also numerically by Panda and Pretorius. You know, this is all very recent, but the method seems to be that for investigation of shocks, BDNK has advantages over Israel-Stewart. However, I'm not going to tell you about shocks specifically. I'm going to tell you about something a bit more general. I want to ask the question that's kind of a standard question we ask in fluids is that can singularities form in finite time from smooth initial data in Israel-Stewart or BDNK? Sort of the sort of breakdown of solutions. And that's my next theorem, which says the following. There exists an open set of smooth initial data for the Israel-Stewart equations, for which the corresponding unique smooth solutions to the Cauchy problem break down in finite time. Such solutions, such data consists of localized perturbation of constant states. So they are localized perturbations, but they are large perturbations. Okay. Now, some of you might say, what do you mean by smooth solutions? I thought you had proven local opposing Rolling-Gevray spaces. That's correct. But remember, in the case where you don't have the heat flux nor the viscous shear stress, in that case, you can get local opposing in Sobolev spaces. And from there, by standard argument, you can get smooth solutions. And that's the case we treated. So just an idea of the proof, we just follow some well-known strategy that goes back to the work of Gould, Tavildar, Zadek, their work of the relativistic Euler equations. We assume that the solution exists for all time. We derive some quantitatively precise estimates for the evolution of the viscous correction to the pressure, and then you derive a contradiction. Okay, so these are argument by contradiction. Now let me point out this is a proof by contradiction. Therefore, it says that solutions cannot exist for all time, but it does not reveal the nature of the singularity. It does not tell you what goes wrong. Nevertheless, this is the first breakdown result for Israel-Stewart. So this would be like, you know, the starting point to try to refine this result and try to study now the nature of the singularity. Okay, in sum, I think, and I hope I convinced you, that this is a very exciting time to study relativistic viscous fluids. There's a lot of things happening with data coming from LAGC for the quark-gluon plasma, and now we're going to have data coming from neutron-star mergers. So it's going to be very interesting. So let me tell you about some open problems, things that can be done. There are many open problems because the mathematical treatment of these viscous relativistic fluids is only on its infancy. One important problem is to actually establish local opposedness for Israel-Stewart in subbolide spaces in the full cases, right? When the shear, viscosity, or the heat flux, or both are non-zero. As I said, we have this breakdown solution for Israel-Stewart, but we would like to understand the mechanism of breakdown. It is a shock, it's another type of singularity, something, I don't know, right? What goes wrong? Can we try to also prove something similar for BDNK? Is there a breakdown result for BDNK? On the flip side, instead of breakdown solutions, you can ask about the existence of global solutions, okay? And here, one thing you can do is the following. There are some standard ODE solutions that physicists like things like they're called, like, say, the Gubser flow, for example. So those are solutions that do not break down. What you can try to do now, you can try to perturb the solution and see if you get a global result. And if you're really ambitious, you can try to study the free boundary problem for equations with viscosity, right? Now, even this is something very challenging, even for the case of the relativistic Euler equations. Only recently that has been local opposing has been established. That's a work that I did with Mihaela Ephraim and Daniel Tataro. So a lot more of work would have to be done to generalize this to the case with viscosity. In sum, I think it is an excellent field for those interested in collaborative research among mathematicians and physicists. So the theorem, the mathematics is very interesting, is very rich, is very challenging, but everything is very well motivated from developments that are happening at the cutting edge of physics research. So thank you for your attention.
All right, let's thank Marcelo for this wonderful talk. That was amazing, and let's have time for question. So if anybody has any questions, please go ahead, and ask Marcelo.
Very nice talk. I have a question. So,
yeah,
when you look at this stuff, when it's coupled towards the Einstein equations, maybe you probably know that in constructing initial data, there's the conformal method. Have you guys thought about that at all?
That's an excellent question. Okay, I hope so, but I haven't done. So what we did what people usually do in the evolution problem. We assume that the initial data is given, right? And then we solve the evolution problem. That's a very good question. Of course, it has to be done. Otherwise, this could be a
so
right? It has to be done.
You have to figure out how you would conformally transform all these new variables.
Exactly. You are absolutely right. That's a very important problem.
Maybe
for my next talk, I'm going to put it as an open problem as well.
Yeah, so maybe I'd like to talk with you about that sometime.
Absolutely, I'll be very happy to.
That'd be very nice. Thanks. Very nice talk.
Thank you.
More questions? Do you have more questions? I guess I'll go ahead and ask you some questions.
Sure.
Yeah, so you mentioned, for the BDNK or like Israel-Stewart theory, do you have like some sort of, acoustic metric, like, when you talk about the characteristics and things like that?
Some type of what?
So when you talk about like the characteristics, of BDNK or let's say the Israel-Stewart theory, do you have some sort of acoustic metric, like, I guess it's...
Yeah, okay, so you get something that has the form of an acoustical metric, right? We have more than one actually, right?
Yeah.
And there's a coefficient that appears there that's what defines the velocity, right?
Right.
So that's what I call them would-be acoustical metrics, right? Because it's not like an acoustical metric for the ideal fluid.
Right.
But in simple situations, it's very close. For example, if you look at Israel-Stewart, without shear viscosity and without the heat flux, the heat flow, okay? Then you get only two characteristics. One is the flow lines, of course. Yeah. And then another one is precisely an acoustical metric that looks exactly like the acoustical metric of the fluid, but the sound speed now is the sound speed of the ideal fluid plus something with the viscosity. So if the viscosity is 0, you get exactly back the one of the ideal fluid, right?
Right.
Now, if you have all the other viscosity, then you get several different characteristics. You can always write in the form of like an acoustical metric with some speed, but they're going to be very complicated, right?
Right.
Does that answer your question?
Yes. And also, like, can you? So I never actually worked with Givry spaces and things like that. So can you tell me like what exactly goes wrong with if you start doing with the usual like Solev space local?
Okay. Okay. So because the equations are only weakly hyperbolic. Okay. So right. Think like this. Suppose you want to get estimates for an equation which the wave operator is square. So it's like box u equal to f. Right.
Yeah.
So you're going to lose derivatives, right? Because right, you're going to lose derivatives. So that's sort of the prototype of operator that you get for these equations. Like something like is a product of hyperbolic operators, but the full operator is only weakly hyperbolic. By the way, that's the definition of weakly hyperbolic. It's a product of hyperbolic operators in the usual sense, right?
Okay, so if you turn off the viscous stress and the heat flow, then you can you can gain the derivative back. Okay.
Yes. Okay. Then the operator simplifies. Then you get a legitimate strictly hyperbolic operator.
Right. Great. Thanks. Yeah. Thanks so much.
Sure.
I think even for Einstein dust, you have to use these Gervais spaces. I remember that from Ivan, the work of Ivan Choquebua. You use those things for the Einstein dust equations.
I see. Yeah. But I think nowadays you can do with Sobolev, right? There is I think for the Einstein dust. Yeah.
Well, that was her work from a while ago.
Yeah, I think there's a work of Jared Speck and Mahir Hadzik. I think they did the dust case.
Okay.
Yeah.
Great. Do you have any more questions? Okay. If not, then let's thank Marcelo once again for this amazing talk, and we'll I guess stop recording.